Olivia? 131 PS7, huh? Yeah. That's a lot of problem sets. You still have a month to go. Holy crow, it's gonna be like 10 problem sets. What's 131? Combinatorial structures or whatever? Sweet. Nice. Hey, speaking of that, Ian and Jonas, don't forget, guys, that midterm 2, it's an oxymoron. Midterm 2 is due tonight. March 30th at midnight is the due date for that. It looks like only about half of you have turned it in at this point. So don't forget to do the midterm. It's easy. Like the midterm's a simple one this time. Just take you like 20 minutes to do. But don't do it tomorrow, because tomorrow is your spring break day, spring break 2, just like midterm 2, spring break 2 is tomorrow. Wednesday is a health day. Don't work on your health day. Just go enjoy yourself. Go to the garden or something and sit outside and enjoy the sun. Should be beautiful tomorrow. Wouldn't it be too late tomorrow? What too late? Oh, for the midterm for sure. So finish the midterm tonight when it's due, and then tomorrow on your wellness day you can go and enjoy. When's PS4 due? April 2nd. You got tons of time. April 2nd. Oh, is it somebody in the in A1 came up with a great slogan? I wanted to put it on a T-shirt. It was something like the due date is the due date, DUE and DO. So basically you start on the due date. But if you start when it's due, then you don't have to work so much on it, right? So you don't spend a whole week on it. You spend a couple of hours of panic on it. Yeah, I know you, Jonas. You got it, man. Strive best under pressure. It sounds like another T-shirt. SBUP. Alrighty. So this week we're going to be in files. Today I want to talk from the C side. How do we work with files? Basically reading and writing files and so on. It's actually really simple. Like you guys will be fine with files. And then on Thursday, we're going to flip it. And on Thursday, we'll look at files from the kernel standpoint. So how's the operating system see a file? What structures are set up for that and so on. Sounds like Quasimodo coming through the door over here. So files all week, basically. And then at some point, I got to push PS5 out to you. Actually, when is PS4 due? The 2nd? PS4, oh, PS4 is due on Friday. So yeah, so probably Monday or Tuesday, you'll be looking at PS5 coming out. PS5 should be a short one. You're gonna work with files, essentially. All right, so, sweet, files, file ops. All right, so the nice thing about Unix is, one nice thing about Unix is that everything in Unix is a file. Technically, they're all streams. A stream is just a bunch of bytes, bytes in motion, basically, a stream of bytes. Because everything looks like a file from the operating system standpoint, all the things we do, like reading and writing and opening and testing and moving, positions around in buffers and so on, those functions all basically work across the entire kernel. It doesn't matter what we're talking about. So for example, if I'm sending data back and forth between a client and a server over a network connection, it's just a stream. It happens to be on a network. Let's say I've got, actually one thing I do often is I write a quick little chat client or a chat server with 2 clients. So you run the chat server, the 2 clients talk through the chat server to each other. Well, in that case, I've got 3 processes running on localhost, for example, and they're using sockets to talk to each other. But again, from the kernel standpoint, it's just a stream. I'm just sending bytes back and forth on the stream. So everything is essentially a file. That's the primary abstraction here. The nice thing about that is that once we've learned some file semantics, like how do I work with a file, a lot of that transfers over to how do I do network calls, how do I move data on a socket if I'm doing RPCs or something. Like all of it sort of translates because it's all basically the same abstraction. And even stuff like keyboards or printers and so on, they're really just, it's just streams of bytes, you know. You write to those just like you'd write to a file. I actually remember, oh my God, this is going back 25 years, 30 years. Back in the 90s, I was actually was writing a book on networking for O'Reilly. And one of the things in the book, I invented this cool little box. I was I was living in a commune at the time, and a lot of us had email accounts on various systems in the commune. And what I created was this little little box that had lights on it. And when you got email, your light would light up. If it was important, like I could parse the headers out. So if the subject said urgent or something, it would blink the light. But like the functionality there was just essentially just opening a socket up and writing a character to it. So, you know, if I had five, or let's say I had eight different lights on the box, where really all I was sending was a character. I could send a character that would set individual bits. Each bit was a light on the box, and if the bit was set, the light would light up. So I just had to figure out, with this combination of lights to light up, what's the character I have to print out to that memory location. It basically looked like a printer, but instead of a printer, there were LEDs hooked up to it. RPC is a remote procedure call, which we don't talk about in here, thank goodness. That's for Professor West's course, 350. Well, so these are basically streams. We're talking specifically about files in here in this lecture, so I'll probably use file more often. But just keep in mind that generically, these are all streams. Very simple semantics on these things. I can open and close a stream. I can read or write to or from a stream, and I can do a seek if I need to. That's kind of it. Like those are the things we're going to do. And fortunately, all of those are fairly well abstracted also. So there are a bunch of file types. Some is just text files, like just arbitrary data sitting in a file in text kind of format. I can also have a binary file. So like I might have an image or a movie or sound or something. That's just going to be straight up binary, just bunches of ones and zeros in some format. I might have a socket. So a socket would be something I would open up between two processes, either locally or local and remote. That socket essentially represents a network connection. If it's local, I don't have to go through the network stack. I can just go through the first couple of layers. If it's a remote connection, then that socket is going to represent a full network stack. But again, it's the same. I just open up the socket, open it, and then start reading and writing from the socket. It's no different than a file, really. Some stuff we're not going to talk about, some esoteric stuff like named pipes. Actually, we'll run into named pipes, I think, because when we start talking about threading and writing threaded code, so I've essentially got more than one thing happening in a process on threads, we can use named pipes to talk back and forth between those threads. So I guess we'll hit that sort of the end of the course. Symbolic links, I said I'm not going to talk about it, but I can just show you what they look like. Symbolic links are really simple. Let's see, do I have any over here? See if there's any in user bin. Yeah, there's a couple here. So here, for example, anywhere you see these arrows, there's an arrow there, there's an arrow here, and so on. In fact, we see them more often in the lib directories. Let's do list-l/user/lib, and I'm going to grep for %ls. So that grep line says, go and do the full listing like this, and then run it through grep, and grep for _l. Caret is the beginning of a line. So this says print out any lines that have an L as the first character. Ah, there's only one. Really? How about user local lib? None, really? Hang on, let's pop over into, that's gotta be some on the Mac side, right? Some on the Mac side now. Oh, and here's some. So I'm looking for symbolic links here. That's what all these arrows are, and they're represented in the directory structure as an L flag. That means it's a symbolic link. The way these work is, let's say I'm linking against this library, libpython, for example. So I'm running some Python code, and there's a bunch of library stuff in libpython that I need. Well, here in user lib, my library directory, that's where I'm going to put libpython. But notice that it really points to a different file. So this is not the file itself. libpython here is not what you think it is. It really is pointing to this thing, libpython 2.7. So this is sort of the generic version of it, right? Oh, I need libpython. Well, what version is it? That's the symbolic link. And the beauty is that, let's say I was linking against this. Actually, here's an even better example because I could link against that. Here's standard C, like libstandard C, actually libstandard C++. So a whole bunch of C library functions in there, right? Well, I'm linking against version 6 of that file. Well, what I'm really linking against is version 6.0.9 of that file, like it's a specific point release. The beauty though is that when I link my code, so I'm in C, I do a compile, it does the linking, it's gonna link against this. At runtime, when I need that, so this is a dynamically linked library, I'm just gonna go and get those references at runtime. Well, right now it's pointing to version 6.09, but let's say next week I upgrade that to version 6.0.10. It's a different version, right? But I don't change this. So I'm still linked against that. And when I run my program, it's gonna look here. It's gonna realize, oh, what it really means is this stuff. Now it's gonna go look in that file for me. So it's a level of indirection, basically. I can abstract out the version of that library and just point to the correct version down here, but expose this version. So that's a symbolic link. You would use ln, the command ln to set those up. So here's the man page for ln, and you can see that S gives you symbolic links. And we'll actually, Thursday, when we start looking at files and directories from the kernel side, we'll see where the flag is to say that this is a symbolic link. It's just a flag and a header in the file descriptor. So we're not talking about that. All right, let's talk about regular files. So we make a slight distinction in Unix between text files and binary files. The big difference is that in a text file, there's an end of line indicator to tell me where the end of the text line is. In binary files, there's no end of line because it's just a stream of bytes, just ones and zeros. So it doesn't really make sense to have an end of line there, like it's an image or something. The only bug, it's not really a bug, the feature that we're worried about is that most of the world marks the end of a text line with a /n character. Windows does it differently than everyone else. It kind of doesn't matter to us unless we're trying to write code that's portable. So if I'm on the Unix side and I'm writing code and I know I'm going to deploy on a Windows machine, I got to deal with this. And what I probably will do is I'll normalize the file. So I'll open the file in Windows and I'll normalize the file, get rid of the XDs, and only leave the \n's, the XAs, just to make it like a uniform look. And then I will go ahead and run the rest of my code. I don't know why the devil they did that. There's a slide somewhere about this at the end. This really bit my ass once. A client, I was a developer at that point, and doing coding. We were coding on Unix, but deploying on Windows. So we were coding up on Solaris, which was a Unix variant, and then we were deploying on Windows NT. And we didn't realize that there was a file structure difference between the two machines. Like, who would think that you would write a file differently, right? And so for a long time, like, we kept crashing at random. We couldn't figure out why. And finally, we got deep into the debugging weeds and realized, holy shit, like, there's an extra character at the end of every line on this Windows side. We ended up writing utilities that would, it would just make them work, right? So if we're on Solaris and deploying to Windows, it would add the /R. And if we're going the other direction, try to read stuff from the Windows side, we'd have to get rid of the /R. So we had just little utility routines that, looked at the file to see what kind it was and then did the right thing. But what a pain in the tuchus that was. All right. There's some things that we can get without going too deep into the file system. Like, we can talk about the size, and we get timestamps like created, updated, that sort of thing. We can get those from C. If we want to go deeper than that, we're going to start looking at kernel structures, and we can get to that information from C. It's just an extra step or so. We'll see some of that on Thursday, I guess. Let's see what else. Yeah, I mean, normally just reading stuff, right? We're reading stuff from a file into memory, or writing stuff from memory into a file. The common thing is it has to be in memory before we can work with it. So I got to read it in or push it out. And then the kernel itself keeps track of where it is in the file. There's going to be an end of file flag set. Anytime I try to access a file past the bottom of the file, there's a condition flag set, EOF. I can test that. And in fact, you'll see in a couple of slides, the common read paradigm is open up the file and then put it in a while loop. The while is while not end of file. If I try to read something and it's past the end, I get an end of file back, and that'll shut down the loop. So we'll see a lot of that in our code, while not end of file. And it's that end of line problem. The Windows versus Unix end of line. Let's talk just briefly about directories and like how they're laid out. So there's usually a root of the file system, that's /. And then below that, the directories are laid out in a tree structure. We can traverse this tree from the root. So if I wanted to get down to hello.c, it would be /home/dro/helloc going down this tree. User includes sys unistan.h /user/include/sys/unistandard.h, and so on. And from the kernel standpoint, directories are very similar to files. They just have a special layout that tells me what's in that directory. So it's a file in the directory system that has information about the directory. It's meta information. There are two ways that we can address something like a file on the file system. One's with an absolute path. So an absolute path is going to start with a / being the top of the file system up here. Anytime I see a / at the beginning of a file name or a set of directories, I know that I'm starting at root, and that's an absolute path. The other version is a relative path. Relative paths use dot and two dots to indicate motion in the directory structure. So for example, here I am, I want to go to /home, CD is change directory. That'll take me right to /home. If I'm in a directory that has a subdirectory called dro, change directory here, dot means here, look in here for a directory called dro and then move there. And then dot means the parent directory. So here I'm catting something out. Cat just means print. So go up a directory, look for a subdirectory called dro there, go in there and look for hello.c. So for example, I'm here, so I'm over in /users/paryd. If I want to see what's in users, I just say list dot will go up a directory and show me what's in users. Not much in there, it's just shared in paryd. If I want to see what directories are in here, Rep %d caret is, or caret d, caret is the first character in the line. If it's a directory, it'll have a D there. Here's all my directories. And we can go down to Postman or something, or data stuff in here. Any directories? Thank you. Dash L. Oh, it's one journal. So I've got a bunch of stuff on here, and I could go up a couple, cd dot dot slash dot dot. That'll get me to back to users per ID because I was two directories down. Jonas asked, it also works well without the dot slash dro, right? Yeah, if you're this there, like here, if I look for directories here, so I'm here, if I want to go to downloads, I just do cd downloads. Just like that. That works, and this works also, here slash downloads. You are correct, Jonas. All right, so that's directories. And we'll see what that looks like again from a kernel structure standpoint on Thursday. Why would I ever use the dot then? Jonas, you might not know what directory you're in, and like programmatically, you might just want to use dot to make sure that you're always looking in the current directory. You probably wouldn't, like just from a command line, you're probably not use that from the command line. How about operations, open, close, read, write? So these four things, these are all essentially abstractions coming out of standard I/O. These are all going to start with an F to stand for file. Really means stream. They should all start with S, I guess. But what's happening here is I've got a set of abstract functions. It's actually a really nice feature. Like here, these things, all these Fs, fopen, fread, fprintf, and so on, all these things are exposed in standard io.h. So those are coming into C. When I call fopen, what's really happening is another function call is happening on the kernel side. I'm calling a function called open down in the kernel's libraries. So there's an abstraction. It's one of the few abstractions we have in C. Most of the time in C, we're like really down in the metal, and like there's not much room. It's like what we see is, oh, that's oh, that looks like memory, like it's just right there. Here though, there is a layer of abstraction, which is great because if you think about it, like Unix is Unix is just software, right? It's just a program that's running on some hardware, and it abstracts out the details of the hardware for us. So these open, read, write, and so on, these are really low-level routines. They're going to be working at the block level. So we haven't seen how stuff is laid out in files, but it's laid out in blocks, sort of like memory. So I'm going to go from block to block to block. I might have to like move to a specific block in a directory and so on to do a write. I don't have to worry about any of that in C. All I have to do in C is open a file, open a stream, and then start writing bytes into it. I don't have to worry about the underlying structure of it. That's handled by open write. So all the nitty gritty, ugly details are abstracted out for us, and we get this nice clean functions, fopen, fread, and so on. That abstraction layer that's a really common thing, even within the kernel, like within Unix. Actually, I guess that's part of the abstraction layer in Unix. Most operating systems have an abstraction layer where they hide the details of the hardware from either the operating system or the software on top of the operating system. That's what's happening here. And that abstraction layer, that's actually a fairly new thing. Like it used to be, let's say I was going to port an operating system from one machine to another. I have to rewrite most of the operating system to do it. And then I guess it was sort of the late 70s, early 80s, folks started working on, especially large operating systems, adding abstraction layers. So Dave Cutler, for example, worked at Digital Equipment Corporation, same building as me. He was the architect for VMS, the operating system. Actually wrote a bunch of systems courses for that operating system. But Dave was big into abstraction, And he took that idea to Microsoft. So on the Windows side, you'll see Windows NT and everything from that point has what's called a hardware abstraction layer, HAL. And that abstraction layer contains functions like open, read, seek, and so on that hide those details from us. It makes it really easy to port the operating system now, because really all they have to port is these small utility functions. As long as they work with the correct hardware, the rest of the operating system doesn't change. Abstraction is always your friend. That's so weird. I love abstractions, like especially when I was working as an architect. Like that's all I talked was just abstractions. But I also love C. Like it's really fun writing in C that has no abstractions. Kind of weird. All right, so let's talk about opening files. Opening a file, it's the fopen function out of standard IO. Basically, I just give it the name of the file that I want and what access mode I'm interested in. So if I want to do a read, it's R. Here down here in this example, I'm using fopen. That's the name of the file. And W is for a write, right? Yeah, I'm going to write to it. Nice, bring up the table. If I wanted to read that data file, I'd have an R instead of a W here. Like that's kind of it. Now, there are error conditions, of course. Fopen is going to return a pointer to that file for us. It's actually a pointer to a file descriptor that contains information about the file. And actually, those file descriptors, those live on the operating system or on the file system itself. If you look over in, let's go back into the container because I don't know where the proc subsystem is on Macs. So what's going to be? It's going to be Docker exec. Give me a terminal for it. And we're in CS210 client, and I want bash. All right, so here's a prompt over on the container. Let's go look at the proc file system. cd/proc. So again, we're starting at root, and then there's a subdirectory under that called proc. Here's what's in it. This is actually a pseudo file system. This doesn't exist on the file, like it doesn't exist on the disk itself. This is a memory structure. /proc is mounted by the kernel, and it contains information about the running operating system. So anything that you need to know about the kernel's operation is going to be in /proc. If I need to know, for example, well, what file systems do I have? I've got a file systems entry here, right? Right here. Just cat it out. Those are my file systems. These are the ones that I have access to, not necessarily the ones I'm using, but this is what the kernel knows about in terms of file systems. If I want to know, let's go and look at FS. See, FS is going to be the file system itself. So this is information about the individual file systems. And let's take a look at CIFS. This is like configuration information for the CIFS file system. Cat stats. And that's a file called stats. So I see things like how many mount targets do I have? How many SMB requests have I done? SMB is, what the hell is SMB? I'm embarrassed because I literally wrote a book about this called File Sharing with Samba. SMB is Session Management Block. It is a protocol that Windows uses to share files with Unix because they're in different formats. If I want to know what, like information about an individual process, let's go back to /proc. It's been a while since that book came out. I think it's not even available anymore. So these numbers over here on this side, the numbers 1, 10, 15, and so on, those are process IDs. I can find process IDs by doing a PS. So here's the PIDs. PID is process ID, 15, 10, they correspond up here, right? So if we go and look at Here's 450 is this bash session. That's the bash session that we're running. So let's go look at 450 in the /proc directory. And here's everything about this process. So this process is the one we're in the terminal in. This is all just data about that process. So what's the command line? Cat command line. /bin/bash was what we're using. What network resources am I using? How about file system stuff? Let's try FD for file descriptors. So I've got 3 files open in this process. I've got 0, 1, and 2. The descriptors 0, 1, and 2 typically correspond to the standard in, standard out, and standard error. 0, 1, and 2, in, out, and error. They're all the same. They're all pointing to dev PTS0, which is the console. So file descriptor 0, if I write bytes to standard out, that's file descriptor 1. If I write bytes to that file descriptor, it's going to end up on the console, but it looks just like a file. So I'm just writing bytes to that file. And then I've got, I don't know why 255 is there. Cat 255. Yeah, I don't know what that file is, that descriptor with 255. FD, I went over to the FD info directory in /proc, and it's showing me, I did a cat on that file. It's basically so the flags are going to be things like, is it protected? Is it a system file, like that sort of thing? The mount ID is used by the mount command to show me where the file is mounted. And then what position am I in the file currently? I'm in position 0, which is the top of the file. So nothing's basically nothing's happening with that file. It's just sitting there. And by the way, all this stuff in proc, so cat CPU, for example, here's all the information about the CPU. There's load stuff in here. If you've used the top command ever, if you ever use this command, all this stuff, information about the load on the CPUs, what processes are running, how much memory they're using, all of that stuff, all of this comes from the proc directory. And the proc directory is just a memory structure built to look like a file. Well, actually, that'd be a really great lecture, wouldn't it? Just to do a top, like a long top, and talk about what all of these things mean. That's pretty useful information, I think. I have to remember to do that. Because all of this stuff is useful to us from the system side. Like, this is all stuff we need to know. All right, cool. All right, so I'm going to get a file pointer back from this thing. That file pointer is defined in, declared rather, in standard io.h. And again, it points to a structure that contains information about the file. If there's an error in opening the file or reading or whatever, if there's an error with the file, that file pointer is going to end up being null. So we have to be really careful. We're talking about just what I showed you. We have to be really careful about error checking and files. Like in C, right, there's no hand holding, so all the error checking is on us. Well, one thing that we have is that file pointer. We also have this thing. If I like, sometimes I'll do a command like, here's this fclose function. Fclose is out of standard io.h. It just closes a stream up, and that's the name of the stream. It's going to give me status back. So a 0, generally in Unix, 0 means success. If I get anything that's not a 0, so non-zero, especially a negative number, that's going to mean there was an error. And so I can just capture that in status and then do something about that. You know, I might, try to go and figure out what the error was with p error or something, which we'll see in a sec. It's really, really important to close your files. There should be matching opens and closes in your code. If you forget to close a file, theoretically, the operating system is supposed to do the right thing, and when your program terminates, all those files get closed for you. I don't trust it. Like, you shouldn't trust it, right? So just close your files. If you forget to close a file and it remains open after the program exits, the data probably can be corrupted. Like, just bad things happen to the data in the file. There's also a limit on the number of files you can have open at any given time in a particular process. And we can see that with ulimit. See what it is here. Ulimit, what is it for files at Deshan? Yeah, so I can have I basically have 1 million open files. And I know that's a lot. Like, we're never going to hit that, right? But just do the right thing. It's a hygiene thing. You open a file, just close the file at the end. Yeah, in problem sets that involve files, if you open a file and don't close it, it's probably going to be 5 points right off the bat. Close your open files. Oh, questions down here. Joyce says, does the file have to be located in the same folder as the project file, or can it be from anywhere? We just specify where it is. So again, it's sort of like assembly language, like we're writing the code, so we know where the file should be. And so you just explicitly say where the file is, either with an absolute path starting at / or a relative path. Usually in my programs, I tend to use relative paths because the program's running in a particular spot usually, and it's going to read my files relative to that spot. Jonah says if you include the file path, it should also work if it's not in the same directory. Correct. So if you have the full canonical path, it'll always go there. Anyway, just remember to always close your files. Ulimit, by the way, gives you all sorts of information. I don't have man here, do I? Here's the man page for ulimit. Unfortunately, ulimit is a bash command. It's probably in Z shell as well. Most of the shells have ulimit in it. And so this is actually all of the commands that are in the shell rather than just ulimit specifically. Does ulimit.h give me something? Yeah, of course not. Bad option. Oops. Ulimit is unlimited. That's handy. I don't know where I would look for. I guess I'd have to go online and figure out what the switches were for ulimit. All right. So one other thing, since we're here down on the command line, I wanted to show you how to pass arguments into main, because in some of the code we're going to look at, the sample code, I'm passing in a file name. So we've been writing main, just int main, and then brackets for the main function. Main actually takes 2 optional arguments. It is basically if I'm running the program from the command line and type in commands like this, if I say, my program is called my prog, and I want to pass in arguments, I would say like foo.text and bar.text. Maybe I'm copying the contents of one place to another. Well, these 2 things are arguments. Bar is an argument, foo.text is an argument, my prog is the name of the program. When I run this from the command line, these, actually all 3 things are going to end up in an array for me, so I can just pick them off and use them. Like this. argv, actually down here, argv is going to have the name of the program. And then argv0 has the program name. argv1 has the first parameter. So here, that's in argv0, that's in argv1, and that's in argv2. And then what we also get from the runtime system is how many arguments were there. So that's argc. Argc is the count of arguments. We have to have the count because it's C, and we can't ask the array how many elements it has, and so we need to know the number. argc is the number, argv is the array of commands. Will argc be 2 or 3? It'd be 3. It's the length of the array, basically. If I'm doing flags of any sort, so maybe I wrote my code so it's like this, like -- source, -- destination, like that. So I'd need some way to figure out, oh, that's a flag, this is the target of the flag, so the source is foo.text, the destination is bar.text, and so on. That's up to me. This would end up as, what, 5 things? So that's argv0, argv1, argv2, argv3, argv4. So 5 things in that array, and it's up to my code to pick these off and say, oh, that was dash dash source. That's what this means. I need to go and read the next thing in that array, and that's going to be the target of the source, and then store that information somewhere in my program and use it. Like, again, it's just up to us to parse that stuff out. And normally what happens, it'll happen to you guys too if you keep on in C. I hope you do, because it's a great language to like be fluent in, and especially in software engineering. You'll end up writing a function to parse out this stuff and then just keep using it for the rest of your life. I've got one of these that I wrote back in the 90s when I was in school. I still use it. You know, it's like, it just, once you've written it once, it always works because stuff doesn't change in Unix very often. And so once you've got a function that returns like key value pairs, you know, source is foo.text, source is the key, that's the value, that's the key, that's the value. Once I have code that returns that stuff, I just keep using it. But it's up to you. It's up to you, up to you. All right, here's just an example. So here's an example of, and there's no error checking here. We're printing out possible errors, but not actually doing anything with them. So here's int main. We're going to pass in the file name here, and I'm going to open it with fopen, file open essentially. We're really opening a stream, but we're working in the context of a file here. Question, is it char pointer argv because we're passing in the names of files and not the contents? Edwin, yeah. Oh, I forgot I asked that question, didn't I? Somewhere I asked, why is it, oh, here. Why is that a char pointer pointer? It's because these are strings in here, and a string is essentially a character array. And so the top of the, like the entry into that array element is going to be a pointer to the first character of the string. And then I got a bunch of them, so I got a bunch of char pointers in the array. Yeah, Edwin, does that make sense? Jonas has it pretty close. So it's an array of character pointers is what it is. That's why there are 2 stars. That'd be a great interview question, I think. All right, so we're opening a file, just using fopen to open it. Fopen takes 2 arguments. It takes the name of the file and the mode I'm interested in. Here I'm opening it for read-write. Fopen, whatever I passed in for read-write, if there's an error, this little p-error function is really handy. So p-error comes out of standard I/O. Any of the utility functions in standard I/O, all the scans, you know, scanf, printf, all the stuff we use out of standard I/O, if there's an error in any of those functions, they set information that p-error can read, and you'll get an actual error string here. So for example, if this thing wasn't on the file system, I would get, you know, no such file or directory here when p-error printed this out. And the string that it takes is just a prefix string. So it would print error space, no such file or directory if that was the error. It's a really handy debugging tool. If something's going wrong with something out of standard I/O, just hit p-error and it'll print what the problem is. Otherwise, you're getting things like, oh, I got a null pointer back. Well, why? P-error can probably tell you why. So we open the file. I get my file pointer back. I called it data in this case. I'm just printing off what were the arguments that I read. So argv0 and argv1, I'm just printing them out here, nothing fancy. But now I'm using fprintf. Just like printf, fprintf works with format specifiers. And so I can use things like %s, %i, %x, and so on. But here it prints to a file or a stream. This is actually the stream. And then this is the thing I'm printing. So it looks just like a printf, right? We're pretty close to a printf. Honestly, like printf is okay. Frankly, I would just use fprintf everywhere, even if I'm just printing stuff out on the console. Just say fprintf standard in, or standard out rather. std out, standard out is the console in most cases. And so just print out to the console and you get all of the format specifier as you want, as you do in printf. fprintf is just a little more robust than printf, and so it's a little safer function, I think. So I'm gonna, this bit, this fprintf is gonna write this to a file that's pointed to by this guy, and then we just close it and check the status. Actually, don't even check the status. We capture the status, but not check it. And then a quick return. Let's go look at that in code. Excuse me. We threw all of this in, so I don't have to do it again. Nice. And let's clean this one up. This stuff we can uncomment. So this is right from the slide. There's a return down here somewhere. Now, one thing is like, how am I going to run this from the command line? There are a couple of ways to do this. Like if we just, like did GCC-O main or something, like it would, I would have an executable, right? And then I could just run the executable from the command line. Usually if we're in the IDE, we're not wanting to bounce back and forth between the command line and the IDE. And so there's a really easy way to give a bunch of parameters to what looks like a command line. I'll show you in a sec how to do it here. Question from Jonas. Why do we save stats if we never check it? Because this is a quick example for a lecture. Normally, if you're gonna check it, like you're gonna save it, like you're gonna do something with it, right? So there'd probably be an if statement around this. Print out, something in a log or something if there was a problem. Here's how you do it from CLion. So if I want to do something like, I basically want to do this. If my program is called foo, I want to go foo here dash foo. That's the program, and then give it a file name, test.txt or something. Like that's how I would run it from the command line. Well, how do I do it from CLion? I would go into build, go into the build menu, sorry, the run menu, and edit configurations. Run edit configurations. And the window that pops up, you'll see there's a program arguments window right here, which is great because that is the list of arguments that you're going to get on that argv array in main. Bar is buzz. Like all those arguments, I got 3 arguments here, right? Here, that's one argument, that's an argument, that's an argument. They're all going to end up in argv for my pleasure. And then just hit apply or just hit OK, it'll apply it for you. And now when I run this thing, it'll take these guys as command line arguments, just as if I ran it from the terminal. What ends up in argc, I'd end up with 1, 2, 3, 4 would be argc, number of arguments. So let's run it and see what it does. Let's build this, build, go run it. And so what did it do? Here's that p error line right here. So error is just sort of the prefix. There was no error, so it just printed success. Then we printed we printed the arguments themselves. So here's the arguments, foobar, fizzbuzz, and so on. Then we're going to print into the file, this is a test, and then close it. Let's go find that file. Looks like it's here, home, CS210/foobar. Copy that. And am I in the container? I am in the container. So let's go here to /home/CS210. I've got foobar.txt, 1852 is just written to. Cat it. That's what's in it. And it's there because you can see that's what we wrote, right? fprintf, this is a test, /n to end the line, and there it is in the file. Jonah says, is there a way for us to check whether P or print something else other than success? Have an automatic error checker? Yeah, and it was on the slide. Hang on. 17. I'm looking for that P error slide. Shout if you see it. All the scripters, where the devil is that? We were just talking about them, right? Opening a file. So slide 17. Were you on that file? Yeah, it actually, there's another one though. There was on a previous slide. What was the actual code? Janice, I'll have to look for it. It's on a slide somewhere in here. So there, yeah, basically there's a way to get the error code. So P error just prints out the current error. Where do we just see those? We're talking about clear. Maybe I'm thinking of the A1 lecture. It's coming up. Yeah, I guess it's coming up. Right to a file. Pure is right on there. Reading from. Oh, here it is. There's a checking for errors slide coming up, Jonas. All right, cool, huh? Like that was pretty easy. And again, we're not doing any error checking here. So, you know, it's a really short piece of code just to write that file. So we do need to write the end of line character if we're using fprintf. When I'm writing to a file, again, I usually use fprintf. There's also an fputs file put string that will put the end of line marker in for you. That might be useful if you're if you know you're just writing strings to the file. Just use fputs s, and that will automatically throw in the end of line character for you. How about reading? So in reading, same sort of idea. We're going to open the file, read some data, and then close the file. We can use fgets instead of gets to get strings out of the file, just like you can use fputs to write the strings. Fgets will read the strings for you, and it'll do the right thing with the end of line characters. When asked, would fprintf fail if there's no \n to the end of the line? No, it's just sending bytes to a stream. So it's whatever bytes you put in that stream. If you forget, then when you do a read, it's not going to see the \n and just keep reading until it finds one. It's like forgetting the terminating null on a string. When you copy a string in memory, it's like you'll just keep going until it finds a zero somewhere. All right, so reading from a file, typically we're going to look for an end of file flag. So there's going to be, when the kernel tries to read the next byte in a file that I've hit the bottom of, it's going to see that it's at the bottom of the file, and it's going to return, or it's going to flip this end of file flag. I can watch that end of file flag. It essentially gets returned by the read, and then just use that in a loop. Like, it's always easier to look at the code, right? So a couple of things about the code. I need someplace to put the stuff I'm reading in from the file. Here I'm just defining an array to stick them in there. It's going to be 100 bytes wide. So I could read basically 99 bytes and a \n, 99 characters and a \n. So I got 100 bytes in there. Now I'm going to open the file for read operations. And it looks like I'm passing that one in. And then here I'm at least doing a little bit of error checking. Like if I got a null back here, so fopen is going to return either the file pointer or null. If there was a null, there was an error. So print out what the error was and then get out with an error condition. If there's no error, then go start reading it. And here's the while loop. So while this, that's basically going to return end of file when I hit the bottom. End of file looks like a false essentially. And so this loop will keep running until I hit the bottom of the file. And in that loop, I'm just going to read a bit of data and then print it out. And then close it. Let's go see what that looks like. Dip, 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 dip. That's this stuff. Always handy to have this pre-positioned. Or here's the code from the slide. And let us, I guess we can just use the same file, right? Oops. Run. Just want to see the config. What is it? Foobar.txt? Great. Let's get rid of these. Doing okay. So foobar.txt is the file we're going to play with, and it should be in home/, right? Run. configuration, it's in /home/CS210, great. Let's go put something in it. There's foobar.txt. It's got what's got it in there right now? Just junk. Let's put some files in there, some lines. Cat into foobar. So this is a line. This is another line. This is the last line. That's the German spelling of that. Control D. All right, so now I've got a bunch of stuff in here. Let's go read it. So it's just going to open the file, and it's going to, notice here's the fgets, right? So I'm using fgets to grab a string out of this file. Where's it going to put it? It's going to put it in data line. So each time that's basically going to be overwritten. How many bytes? Up to 100. So that's the maximum number of bytes to read from that line. And typically you're going to set that number to be the same size as your buffer. Like if that was 102 and I only had 100 here, that would be a problem. If this were smaller, it's fine. It makes sense to set them equal to each other, to the point where I'd probably define that number with a define statement, define max read or something, and use max read here and max read there. And then what file am I looking for? What stream? I'm looking at the input stream, and input is this guy. That's the file that we just opened. So it's just going to read through till it hits the end and print them out. Build and run. There they are. Another line, another line, another line. Simplicity itself, no? All right, cool. Jonas says, so fgets automatically advances. Yeah, fgets. So the thing about that file is, oops, wrong file. Is there a way to look at a file in binary format? What does object dump do? Object dump. Let's try. File headers. Yeah, it's not really an object, so it's probably not going to do it for me. I was interested in. Yeah, I didn't think so. I was interested in seeing the binary representation of the file, so I could see where the \n's were. Basically, when I typed the stuff in, when I did the cat, I did this and said, you know, this is a line. And I hit return. When I hit the return, it inserts a \n for me. So now this is a line \n. GetString, fgetString is going to read until it sees the \n, and it just assume that's the string. It was inserted when I typed it in. But yeah, it would automatically advance. So it just basically gets to the next line until there are no more lines. Other stuff, like we'll talk a little bit about this on Thursday. If I'm working directly with binary data, like images and sound and so on, like just binary files, there's a set of functions that'll let me work directly with binary. I can also, in these guys, open, close, these guys, I can stick a B on those. Oh yeah, for binary files. So I can stick a B, so if I know I'm working in binary, I'm gonna write, I can say the mode is WB. And basically what WB is it starts ignoring those \n characters and just assumes that those are binary data. That might be the only difference. So it really is just a stream of bytes inside that file. That's the block data, binary stuff. Character data, if I'm just writing and reading individual characters, there are versions of put and get, just like the string version, that work with individual characters. So they're just going to read essentially one Unicode character at a time out of that file, or place one in. And then I can do positioning stuff. I got to be honest, I haven't used positioning since literally I was using tape, like tape. and for those, like normally you would mount a tape, for example, and you would want to fast forward the tape to a particular spot on the tape. That would be a seek or set position, usually a seek to that spot. And then if I wanted to go back to the beginning of the tape, I'd call rewind. I assume these are still useful in like non-tape programming. I've never used them outside of reading and writing to tape. So I don't know. Somebody must be using them. Like, why would they still be there, right? I guess you could emulate a tape in memory, make it look like a tape sort of file system, and then use these to move around in it. Yes. Those are like the note says, those would be really strongly formatted records. Like I'd be moving from record to record, but they would be on byte boundaries or word boundaries, like move forward 5 words, and that's where the next piece of data is, that sort of thing. Back to Jonas's question, it's F error that gives you the error code. No, I couldn't think of that. So P error, actually throw P in here too. So that's going to print the current error condition. So if I just want to test the error and see what it was, F error. And then this is the, FP is the pointer to the stream. Should be a file pointer, basically. So the important ones here are, like that's for sure, if there is a problem and I get a null back, for example, from a file operation, I want to know why. I can go and look here and get the actual error code, and I'm the programmer, right? So presumably I can look up those error codes, maybe go to the source code for the kernel and see what the error codes are, and then do something maybe on a switch on those error codes. If I just want to report the error, I can use P error. In either case, I need to clear the error so that the next error that occurs, will be the correct error, and that's clear error here. So after an error occurs, I'll process it usually and then do a clear error on that file pointer, and that gets me ready for the next error. If for some reason you need a temporary file, and it's actually not an unusual condition, I just need some scratch file or some scratch area that looks like a file that I can do reads and writes from. There's a temp file function out of standard IO that gives it to you. It's an unnamed file. You can also get a temp name if you want. I believe is it temp name? Hang on, let's find a line of code here. Temp, yeah, temp name also. So I can use temp name, and it will give me a temporary file name. And those are all the same length. I can't recall what length it is, but you'll get a pointer back to a character array that has a temporary name. It's basically a unique random number that's been generated for you. So I might open up a temporary file and give it a temporary name just so I could use its name. If you don't use a name, just remember that this pointer, that's the only way you got to get to that file, right? If you lose that pointer, you've lost the file in memory, and that's a memory leak. All right, cool. That's sweet, running short today. We just talked about that. That's for your reference. All right, so bottom line on this side, like working with files on the C side is really easy. It's just open, close, read, write. And the parameters for those are really obvious. There are a couple of error conditions that you'll run into. For example, trying to read a file that doesn't exist. And we just capture stuff like that. Essentially, anytime I do a file operation, I also then have to check for error conditions. Files are just really wonky. There's always something going wrong with a file or a stream. And I just need to make sure that nothing went wrong. Most of these things return a null on error, and so I can just watch for nulls or a negative value coming out of like F position or something, and that'll say, hey, there was a problem, and then go and figure out what the problem was and deal with it. but that's like all C, right? Like there's not a lot of hand holding in C. We still have to do all that stuff manually. The nice thing though is that we do have these high level functions like fgets, fprintf, and so on that are the abstract version of the underlying code that the kernel uses. That abstraction is really handy because we don't have to worry about moving forward 6 blocks on a physical disk device. Like, no, the kernel just handles that for us. It's one of the few things that gets abstracted in C. Actually, even memory is not really abstracted in C, although it kind of is. Actually, no, memory is not abstract at all, right? The file system is, fortunately. And on Thursday, as I said, we're going to dig a little bit deeper from the kernel side. We're basically going to look at the structures that the kernel keeps to keep track of files and directories. Like, what do they look like? If I was working with them directly in memory, like what would I need to change to modify stuff like permissions and so on? So that's Thursday's lecture. All right, guys, that is it for today. Don't forget that the midterm is due tonight at midnight, Boston time. There's no extensions on that, so like, there's no automatic 3-day extension on the midterm. No extension. So finish the midterm by tonight. PS4 is due on Friday, and I guess that's it. I will see you all. I will see you all on Thursday. Have a great day off. Please take some time off and enjoy. I certainly am. All right, bye guys. Peace out.